Right. Hi, everyone. So today we are going to be talking about something called intermolecular forces, or sometimes referred to as IMFs for short. Now, if you put on your English or your writing thinking caps for just a second and think about any roots you might have learned at some point, you might notice this root here, inter. And inter just means between. So when we're talking about intermolecular forces, we're really just talking about the forces between molecules. So I do want you to take just a second to think about what might this tell us about a molecule. So I'm going to think for just a second and then turn to your neighbor, the person sitting next to you, and just tell them, what do you think we're getting at here? What is this going to tell us about a molecule? Okay, does anyone want to share what they told their partner or what their partner told them? Yeah, so we're really talking about the strength of these interactions. And this strength of interactions, or lack thereof, is really going to dictate a lot of what we see on the macro level. Some of those physical properties are directly dictated by these intermolecular forces. So there are many different types, and again, specific properties will be affected by these intermolecular forces. And so I think this is something that can feel a bit abstract because we can't necessarily see these intermolecular forces happening in real time. But it's something that's important enough that people spend their entire careers studying this because it's so important for things like chemical reactions and how they take place, but also in biology. So DNA, those double strands, those are held together by a specific type of intermolecular force called hydrogen bonding, which we'll talk about in just a minute. But also, we see these in everyday life, or at least their effects in everyday life. So, the reason that something like water and something like oil move and behave so differently is in large part due to their intermolecular forces. So, I wanted to provide that context before we go into talking about these different examples. So, the first one we're going to discuss is ion-ion. So we can imagine we have two ions, for example, Cl minus and Na plus. And for any of you who already know the molecular formula for salt, you might already know that these interact quite favorably with each other. But we've got that negative charge on the chlorine and the positive charge on the sodium. And these are going to interact in a very favorable way to form our pal salt. So these are the strongest of the intermolecular forces, and you might have an inkling or an intuition as to why that is, and we can talk about that in a little more detail in just a bit. The second example here is dipole-dipole. And I'm going to talk about a special case called hydrogen bonding. And this name is a little bit misleading because it's not actually any sort of bond that's being formed, but I just want to make sure you know that before we start talking about these examples. I want to highlight water here because water is truly the poster child of hydrogen bonding. And so we've got our dipole here, and overall, the definition of hydrogen bonding is that we need a hydrogen covalently attached to either an oxygen, a nitrogen, or a fluorine that can then interact with the electron-rich spots, such as lone pairs, on an oxygen or a nitrogen. And that's exactly what we see happening in our water, where the lone pair on that oxygen is interacting with the hydrogen of another water molecule. And that begins to form an entire network of water molecules where this hydrogen bonding just continues. So you can see, hopefully, why this is a special case of dipole-dipole, because all these water molecules have their own dipoles. It's just that they're all water. But we can imagine instances where we have other molecules that have dipoles interacting with each other as well. Our third example here is going to be ion dipole. So we can have an ion like Cl minus, and then I'm just going to draw a sort of a generic version of a molecule with a dipole. So we have a full negative charge on our chlorine and a positive charge on this molecule with a dipole, and the way I've drawn them is showing the most favorable orientation of these molecules, where we're likely going to see some favorable interactions occurring between that negative and positive charge. Okay. Now, our fourth and final example is van der Waals or London dispersion forces. And this is a bit of a unique case because in all these other examples, right, we've had either an ion with a full charge or we've had a dipole with some sort of partial charge. But in this case, we're going to look at something like methane that does not have a dipole overall and that is nonpolar. But what do you think might happen if we put it in the presence of a molecule that does have a dipole? We're going to see movement of the electrons to the other side of the molecule, forming a partial positive and a partial negative charge. So our methane did not have a dipole to begin with, but now there's a dipole that's being induced by this molecule that does have a dipole. So we would call this a dipole-induced dipole interaction. Now, what do you think is going to happen if we add a second methane? Again, we're going to see movement of those electrons, again, sort of accommodating for that shift in charge. And so now we have a second induced dipole. So that first methane that had a dipole induced within it is now inducing a second dipole. So we would call this induced dipole. And I want that to just sink in for a second because our methane did not have a dipole to begin with. It's all due to the presence of this molecule that does have a dipole and the proper orientation and environment to induce these other dipoles as well. I want to leave some time for questions here because we went over a lot. So what questions do you all have about these forces? Okay, so next what we're going to be talking about is what sorts of properties on the macro scale, the scale that we can see, are affected by this. And we're also going to talk about how we can identify these forces given a random molecule and do some practice problems on how to rank them in order of their intermolecular force strength.